In this vector question, we are given 2 points A and B with position vector given to be A equal to 2i minus j and B equal to alpha k, where k is a negative real constant. And part A of this question wants us to find the angle between OA and OB. Let us write down the information provided. For OA, I'm going to rewrite it as a column vector, which is 2, minus 1, 0. And OB is another column vector given to be 0, 0, alpha. And let us remind ourselves that the value of alpha is negative. To find the angle between two vectors, we are going to utilize this dot product formula given to be A dot B equal to modulus A, modulus B cosine theta. In this case, I will just let the required angle to be beta. All right, and we are going to sub in our A with OA and our B with OB. I will have a 2 minus 1, 0, dot with 0, 0, alpha. And actually for the left-hand side, I did observe that if I were to dot these two vectors together, in fact, I will just get 0 because 2 times 0 will give me 0, minus 1 times 0 will also give me 0, and 0 times alpha will also give me 0. So this gives us 0. This implies that our cosine beta will also be 0. And solving beta will just be 90 degrees. Basically means that OA and OB are perpendicular to each other. Maybe I can just conclude, therefore, OA and OB are perpendicular to each other. All right, in our part B, we are given that the angle of OBA is theta, and it's also given that sine theta equal to half. We are supposed to find the two possible values of theta, and after that, we have to justify which of the two values is the correct value of theta. Maybe I can draw a simple diagram to illustrate this situation. We have O here. Let's call this A. This is B. Let me connect our B and A. And from our part 1, we already show that the angle between OA and OB is a right angle. So therefore, I will just put it as a right angle here. And it also said that angle OBA is equal to theta. So I'm going to write this as theta. It's given to us that sine theta equal to half. All right, making use of our secondary school way of solving this trigo, I can solve that theta equal to 30 degrees or 150 degrees because for a positive sign, the angle will lie in the first and the second quadrant. All right, by observing this diagram, I can see that actually this is 90 degrees. This angle and this angle will also add up to be 90 degrees. So obviously, right, I can see that this angle and this angle are both a cube. Right, I can say something like this. Since angle OBA and angle of OAB must be a cube, this implies that the angle of theta we are looking at is just basically 30 degrees. In part C of this question, it says by considering a suitable scalar product, find the exact value of alpha. The scalar product which I'm going to make use of is this scalar dot product formula. And referring to this diagram, I'm going to make use of this angle here and the two vectors which is OB and AB. Because when we are making use of this formula, we have to ensure that the angle are both pointing inwards or both pointing outwards. So in this case, perhaps I will just consider them to be inwards. So in this case, our A will be my OB and my B will be my AB. Right, let us work out what is our AB first. AB will just be equal to OB minus OA. OB is 0, 0, alpha, minus OA is 2 minus 1, 0. This will give me minus 2, 1, alpha. Let's plug this value into this formula here. My A will just be my OB. OB is this, so I'll get 0, 0, alpha, dot with my, this B here will just be my AB, which is given to be minus 2, 1 alpha, and this will be square root of 0 square plus 0 square plus alpha square. This will be a 2 square plus 1 square plus alpha square, and the angle will be cosine 30 degrees. All right, so let's evaluate this. This will end up to be a alpha square. This will just be square root of alpha square. I have to put a modulus here because this is a square root of alpha square. This will be a square root of 5 plus alpha square. And cosine 30 degrees will give me square root 3 over 2. And for this case, right, I can consider this to be the same as alpha modulus alpha whole thing square, so that this can be divided across. I'll just end up with a modulus of alpha. This will be square root of 5 plus alpha square, square root 3 over 2. Perhaps I'm going to square both sides in order to get rid away the square root and the modulus sign here. I will end up with alpha square equal to 5 plus alpha square. This will give me 3 over 4. Right, multiplying 4 across to the left hand side, I will have a 4 alpha square equal to this. I'll multiply inside, I'll get a 15 plus 3 alpha square. Simplifying, I will have alpha square equal to 15. And solving for alpha, I will end up with plus minus square root of 15. Right, but because alpha is given to us to be a negative value, so of course, we will just be taking the negative value for alpha here. So alpha will just be minus square root 15. I can say that because alpha will be lesser than 0. In our last part of this question, we are given a point C which has a position vector to be C equal to B minus A. And part D asks us to state the shape of the quadrilateral of OABC, justifying our answer. We have C equal to B minus A. I can in fact rewrite this to be OB minus of OA, which is the same as AB. So from here, actually, we can see that the vector of OC is exactly the same as the vector of AB. And referring to this diagram, in fact, I can actually see that our point C is somewhere here. All right, so when I connect this vector to my origin and connect this to B, I can see that my OC actually is exactly the same as AB. All right, in order to prove that it is a parallelogram, actually I already suspected that already, I still need to prove that the vector of OA will be the same as vector of CB, which I can do quite easily by considering CB first, which is the same as OB minus OC. And OB, we can just use B, and OC, we can just use B minus A, which will just simply give me A, which is the same as OA. All right, so therefore we have this condition already. OC is equal to AB, and we have also OCB equal to OA. So these two sides are the same, these two sides are the same. So therefore, I can conclude that OABC is a parallelogram. All right, and the last part of this question also wants us to find the exact area of this OABC. And for a parallelogram, we have a formula to find parallelogram. It's just given by modulus of the cross of these two sides. So from here, I'm going to make use of OA cross with OC. All right, and we have OA, but we didn't have OC, but maybe we can just simplify a bit first. A is just OA is equal to A, OC is the same as B minus A. All right, so we are going to expand this. Is this cross this and this cross this. I'll end up with A cross B minus A cross A. And we know that when two vectors are the same, when they cross together, you just simply get equal to 0. So the balanced terms that I left with is just A cross B. And A I have, B I have already because we already solved alpha equal to minus square root 15 from our previous part. I can just sub in these values. We have a 2 minus 1, 0, cross with 0, 0 minus square root 15. All right, and crossing this out, I will end up with a modulus of, which is equal to square root 15 here, and this is 2 square root 15. This is 0. All right, working this out, I should be able to get a value of square root 75. Simplifying further, I will end up with a 5 square root 3.